For decades, we've basically dreamed of having a direct line from our minds to our machines. I mean, a way to control a computer or a robotic arm, or even just communicate by thinking. Well, this isn't sci fi anymore. It's the very real, very exciting field of brain computer interfaces.
Just take a second and really think about that. What if your brain could just talk to a computer? What would you even do with that kind of power? This one simple question, well, it's the engine driving some of the most mind-blowing neuroscience happening today. It's the whole idea behind a brain-computer interface, or BCI.
But here's the thing. Getting our brains and computers to have a meaningful conversation, it's not simple. For years, researchers have been stuck, facing this really fundamental choice, a dilemma that's kind of held everything back. So just to make sure we're all on the same page, a BCI is any system that cuts out the middleman, our nerves and muscles, to create a direct link between what your brain is doing and some outside device. And that dilemma I mentioned, it all comes down to this. On one side, you have invasive BCIs. We're talking about implanting electrode arrays directly into the brain. The upside, they are incredibly precise and super fast. But the downside is huge: brain surgery, risk of infection, and the implant itself breaks down in just a few years. Okay, so then on the other side, you've got the non-invasive options, like an EEG cap that just reads brainwaves from your scalp. Totally safe. But the signal, it's weak, it's fuzzy, and it's pretty unreliable. So you've been stuck with this choice: high risk for high reward, or low risk for pretty low performance. That is, until now. So what the field desperately needed was a third option, a way to get that high-quality info from the brain, but without all the dangers of major surgery. And you know what? Scientists found a candidate in a place you would never expect. That's right, ultrasound. I know, right? The exact same technology we use for medical imaging is now being totally reimagined as this incredibly powerful tool for neuroscience. It's turning out to be that perfect middle ground, offering a whole new way to bridge that gap between mind and machine. And this technology, it gives us two powerful new ways to interact with the brain. The easiest way to think about it is like this. One method lets us read thoughts, and the other one lets us write signals that can influence brain activity. So let's start with reading. This first method is called functional ultrasound, or fUS for short, and it is a completely revolutionary way to, well, literally see our intentions as they form in the brain. Okay, so how does it actually work? Well, it's this really clever four-step process. First, let's say you decide to move your arm. Neurons in a very specific part of your brain start firing. Then, step 2, your body automatically responds by sending a little rush of blood to that active spot. That's a process called neurovascular coupling. And here's the key. Functional ultrasound is sensitive enough to detect these tiny, tiny changes in blood flow. Finally, a computer algorithm takes a look at those blood flow patterns, and it decodes what you were planning to do. It's not really reading your mind. It's reading the physical echo of your thoughts. And listen, this is not just some wild theory. There have been landmark studies with non-human primates that have used this exact technology to successfully decode the intention to make specific movements in real time with really amazing accuracy. And when I say impressive, I mean it. We're talking 60 to 85% accuracy in telling the difference between 2 and even up to 8 different intended movements. For a technology that's only minimally invasive, that is a massive leap forward. Okay, so that's how we can read from the brain. But what about writing to it? This is where that second ultrasound method comes into play. It's called transcranial focused ultrasound, or tFUS. So tFUS basically flips the script. Instead of listening for signals, it sends these targeted, low-intensity sound waves into a very specific brain region. Now, this doesn't create new thoughts or anything like that, but it can gently nudge or modulate the activity of neurons, making them a little more or a little less excitable. So why would you want to do that? Well, imagine you're using a standard, non-invasive EEG cap, right? And the signal is really noisy. By using tFUS to target just the right brain area, you can actually boost the quality of that signal. Or you could help a user focus their attention, putting them in a better cognitive state for the task, which could ultimately reduce errors. It's kind of like a booster pack for the BCI tech we already have. This chart here really clarifies the two different approaches. On the left, you've got fUS, and its job is reading signals. It's a pretty complex system, and it usually requires a small acoustic window through the skull. Then on the right, you have tFUS, and its job is writing or modulating. It's less complex and can work non-invasively right through the skull. So, two different tools for two very complementary jobs. Okay, so I know this all sounds incredibly promising, and honestly, it is, but we have to do a little reality check here. This technology is still super young, and there are some major hurdles we need to clear before it's ready for prime time. First and biggest obstacle, the human skull. It's like a natural fortress, blocking and distorting the sound waves. Second, there's a built-in speed limit. Because fUS depends on blood flow, there's this unavoidable delay, about 1 to 3 seconds, between when a neuron fires and when we can actually detect it. Third, these systems create a data tsunami. We're talking gigabytes per second that requires some serious computing power to process. And finally, there's the human gap, the most amazing results we've seen so far in animal studies. We've still got a long way to go to make that happen in humans. And just to put this all into perspective, of the core research papers in this whole area, a staggering 80% were published in just the last couple of years. This field is moving at lightning speed, but it's also brand new. We're really just at the starting line.
So with all those challenges, it's a fair question to ask. Is this all just a cool idea that's never going to leave the lab? Is it all just a dream?
Well, the researchers in this field, they don't think so, not at all. In fact, they have a really clear vision for the future and a roadmap for how to turn this dream into a reality.
So here's the game plan. In the near term, the big focus is on hybrid systems. Think about it. Let's combine the amazing spatial precision of fUS with the speed of a classic EEG. You get the best of both worlds. Then, in the midterm, it's all about miniaturization. We've got to get this tech out of bulky lab equipment and into small, wearable devices. And for the long term, the ultimate goal is widespread human validation, the huge clinical trials that are needed to prove this is safe, effective, and actually ready to change lives. And at the end of the day, that is the entire point. The goal isn't just to make a cool tech demo, it's about building something that's robust enough for daily life, reliable enough to be truly counted on, and accessible to the people who stand to benefit the most, people with severe motor disabilities or neurological impairments. Ultrasound might just be the key that finally unlocks the next generation of brain-computer interfaces, creating a much safer and way more powerful link between our thoughts and our technology. And that leaves us with a pretty fascinating question to think about. How will we interact and create and connect with the world when the very boundary between our minds and our machines starts to dissolve?